And we had some equations that we were working on, and the main equation is the momentum equation. It says that. Let me see if I should review the concepts. That might be of some benefit to you. Let me just write down the concepts of momentum and energy in case I missed some of them. I'll just write them here. Work and energy. And these will be on Blackboard, so don't feel like you have to write everything down. I'm just trying to give you a sense of the differences between impulse and momentum and work and energy. All right, so first of all, the equation. T1 plus V1 plus U of non-conservative forces. Okay, so again, remember a conservative force is V1 plus V2. Conservative force, you get it back. That's where gravity and springs come from. Non-conservative forces, you don't get back. Pushing, pulling, friction. Okay. Impulse momentum, we have mv1 plus the integral of f dt is equal to mv2. Okay. And I don't have to write down all these terms, but recognize again, u non is equal to the integral of f ds. Okay. Remember that this is good for force, speed, and distance. And this one is good for force. I'll call it velocity because we're going to continue using it in both x and y, and time. So anytime you have a time problem, you might want to consider momentum if it's constant force or force is a function of time. All right, and both of them have endpoints. And endpoints is the beginning and end of the problem. And what that means is, again, you don't care so much about what happens in the middle of the problem. All you care about is the beginning condition and the ending condition. Okay? All right, in both cases, you draw free body diagrams, of course. And, over here in work and energy, consider only non-conservative forces. Again, this can be confusing. Only non-conservative forces, and the reason is because gravity and springs are potential energy. In impulse and momentum, you have to consider all forces. All forces in the direction of motion. Okay? Can't beat my hieroglyphics there, that's what I'm trying to say. Consider all forces, including gravity. We generally aren't talking about any springs. Actually, we're going to talk about a spring thing today. But it's not going to be the momentum part of it, it's going to be the energy part of it. Anyway, so in strict momentum problems, we're not going to have any springs. Okay, with that, let's do a little more complicated impulse momentum problem than we did before. So let me just draw it on the board since I don't have a picture of this one. It's not that much more difficult, but just something else to consider. Let's say that you have a vehicle, a little cart. Maybe it's a little coal cart getting towed out by a coal mine or something like that, and it is hooked to some motor, and the motor's winding it up and pulling it up the hill. Except that its initial condition is V is equal to 5 meters per second down the hill. That's the initial condition, is 5 meters per second down the hill. The mass is equal to 400 kilograms, and the force in the motor is equal to 3,200 t squared. Okay? Velocity initial is 5 going that way, and we want to find the time that it takes to make it stop. Okay, so a momentum approach would be a good approach, I think, because we've got time, force, speeds involved, velocities. So let's define a positive direction. That's the first thing we would do, is find positive. So I'm going to call this positive x and y going up the hill, and I'm going to go positive force this way. We're going to draw a free body diagram, and free body diagram suggests that we have mv coming down. Sorry, mg coming down. We got an mg. This is at some angle. What's my angle? Ooh, this is a funky angle. This is at 17, 8, 15. Okay, so that's one of those 3, 4, 5 type triangles. 9, 12, or no, what is it? 5, 12, and 13. That works too, or something like that. Is it 5, 12, and 13? Something else? Anyway, 17, 8, and 15 works. But down the hill we have an mg sine theta. Okay? All right. What else do we have here? We got mg cosine theta, but that balances with a normal force. So those are both normal equals mg cosine theta. Did I miss any forces on here? Well, I guess I better put the force in the motor right there. That force, so we know what we're doing. Okay, so we want to find the time that it takes to stop. So it's going backwards first. So we need to figure out what that time is. So let's write our momentum equation, mv1 plus the integral of f dt equals mv2. And we can suggest that, just like in energy problems, if we know what is happening, we know that our ending condition is 0, and we just make that equal to 0. We have defined positives going up the hill, so I have a beginning speed going down the hill, so my beginning momentum is negative 400 kilograms times 5. Okay, that's my beginning momentum. All right, how about my energy? Or not my energy, my impulses. I have in the negative direction an mg sine theta. And in the positive direction, I have that force going up the hill. So I'm going to add both of the forces together under the integral. And I'm going to go plus the integral of 0 to t, because I don't know what time it's going to take. I'm going to say that is 3200 t squared. Minus mg sine theta, and sine theta is equal to 8. That's theta right there, so it'll be 8 over 17, isn't it? Mg sine theta would be mg 8/17. That would be the sine theta. Okay. And those are both under the radical, or under the integral, so those are both dt equals 0. So I got minus 2,000, and I got plus 3,200 t cubed over 3 from 0 to t, so that's just t cubed since it starts at 0, minus mg is 400 times 9.81, 8/17 times time. Okay. You can simplify that a little bit more, do a little algebra, I guess. How would you solve that? Got a cubed function in this one.
With a TI-89.
The TI-89?
Factor function.
You would use the solver, yeah.
You factor in find rational zeros.
I guess you could. You think you could factor that? I don't think I could very easily. I don't know. Maybe you could. If you're good at that, then good. You get 3 roots, or you get something, 3 peaks, I suppose. If you did a cube factoring.
How would you do it?
I would do it on my 89, except I did it on my 83. I would do the solver. All right, so this is just to let you know, solvers are fair game. This is a very typical, very easy kind of problem if you know how to use your solver. Figure out how to use the solver. If you don't know how to use it, the next exam is on the table. It's not going to, maybe not going to guarantee it's going to be given, but I'm just giving you fair warning. Please learn the solver if you don't know. All right, so cube function, solver. Make sure you can do it. T is equal to 1.686 seconds. All right. Now, you can keep on going and say, what's the speed after 2 seconds? Once you have, you you could just plug something in here and go from 0 to 2, and then you could have solved it straight, and that would have been fine. Okay, but anyway, I just wanted to show you that solver is legal and fair game, and I hope that you don't have any questions about that. On Blackboard, like I said, there's a couple of tutorials, but I'm sure you have a friend that can help you learn how to use the solver in case it doesn't work for you. Okay, I want to move on to the conservation of momentum, which is the next section. And we're going to continue on with this kind of assumption stuff and just give you a couple more things to think about. All these things still apply, of course. But when you have sometimes you have a system of particles. You'll have more than one that you have to consider. Let us talk about single particle versus systems of particles. Okay? So let's write mv1 plus the integral of f dt is equal to mv2. Now, for a single particle, that certainly applies. For a system of particles, we would have the sum of in each of those. But when you have multiples, then you have to, oftentimes you'll have different masses and different speeds. So we'll say sum of mv ones plus the sum of the integrals of f dt equals the sum of the integrals of mv2 for systems. Okay? Now, in systems and in singles, we have external forces. An external force is something that causes our system to change momentum. So that would be one of these guys, the integral of f dt. So if you have a system, either a particle or multiple particles, and you have an external force, then it would cause a change in momentum. All right? So these are going to be causes delta mv of the system, external to the particle, or system. All right. I guess that's why I have system, external there. But let's contrast internal forces. What is an internal force? An internal force doesn't really occur in singles, but it does occur in systems. An internal force maybe by the name is internal to your system. And they act equal opposite on each other. On each other. And when things act equal opposite on each other, you ignore them. You ignore internal forces. Okay? Now, erase that last statement, because you don't always ignore them. You ignore them on. All right, I will give you. Just erase that. I'll get to the caveats on that, because I just thought of a kind of an example where you don't actually ignore them, but you treat them a little differently. Okay, so internal forces act equal opposite on each other. Negligible forces. Negligible forces. And these are very small compared to, we'll call it the main forces. And I'll give you some examples of things that are negligible. But basically, the integral of f dt is this force. And so either the force is small, or the time is very small. Okay? So if you have something in a system, very small force compared to the big forces, you can generally ignore that. And or at the time that through which it acts is very small, then you can ignore it. So either the force or the time. Okay, let's talk about some examples. Let's talk about negligible forces for just a real fast. Let's say you have a momentum is really good for guns and cannons and things like that, and we'll be using those as good examples. But let's say you have you got a bullet in a rifle barrel or something like that, and you give it some impulse, some integral of FDT, and it's going to end up having some big MV as it goes out. If you fire it straight up, it's got an MV1, which is 0, plus the integral of FDT is going to be an MV2. All right? Now, the force pushing it up is really, really big because you're going to have a huge MV when you get down to that. However, you also have gravity. Remember, you have to consider all the forces. So you have that integral going up. You also have an mg times time coming down. Well, but realistically, the force pushing it out of the barrel is a whole lot more than the mg pulling it down. So you can ignore the internal force in a situation like that, or you can ignore the negligible force. If this mg is really small compared to this integral of FDT, then ignore it. You don't have to worry about it. Another example would be, say you're firing a bullet going sideways. Let's say you got it now, and you got some integral of FDT, and you got some velocity going out. Well, there's also some friction, isn't there? And you could have a normal force and a force of friction here. But again, the integral of FDT of the explosion will operate over some period of time as it accelerates out of the barrel. This friction force also operates through the same time, but the friction force is going to be so much smaller than the explosion force that you can ignore it, right? So look for opportunities where if problems get kind of complicated and you put all the forces on there, you say, well, I wonder if I can ignore any of these things, because sometimes you can, okay? All right, so we'll mostly deal with the differences between internal forces and external forces. An external force causes a change in momentum to our system. Now, systems have a center of gravity. So if you have two particles in your system, there's a center of gravity of that system. And any external force to our system would cause a change in momentum of the center of gravity. In a single particle, you don't have to worry about a center of gravity so much because you just have one particle to worry about. Does that kind of make some sense?
Yeah.
All right. Let's talk about an example here that's kind of a good one. All right. So here we got, there's probably in your book, I used this one last semester, so I'll just use this again, but there's one in the book just like it. Let's say you have this car on a barge, or a ferry, or something like that, whatever you want to call it. We'll call it a barge. But it weighs, it has a certain mass. The barge has a larger mass. And then it's at the end of the barge, and instantly it begins going 4 meters. Excuse me. At some point in time, it begins driving, and it now has a speed of 4 meters per second going to the left. Okay. Let's find out the speeds of each of them after it starts moving. Okay. So, I don't need to keep all this stuff. We have a system of two particles now, and barge is a particle, and the car is a particle. So, let's all right. So the car attains a speed of 4 meters per second going to the left. And you can see that there's got to be some impulse driving the car, isn't there? So there's some integral of FDT pushing the car that way to get it up to speed. Well, the ferry has the same integral of FDT pushing equal and opposite back on it. So within the system, those integrals of FDT, regardless of what the force is, regardless of what the time is, they're internal to the system. They cancel out. They're equal opposite. So you don't ignore them. I didn't mean to say ignore them. Yet generally they cancel. But you might have to consider them anyway. But anyway, they would cancel out in a situation like this. Okay? So let's find out how fast they're going to go. Well, we have two equations that we're going to be using, two systems of equations, the momentum equations and the relative motion equations. So let's talk about relative motion to start with. Let's define a positive direction. Let's say that that is positive, and the barge is going to be moving that way, the car is going to be moving to the left, which would be negative. So let's call it velocity of the car is equal to the velocity of the barge plus the velocity of the car with respect to the barge. Okay? And these are all vectors, because we'll have to keep track of the i's and j's to make sure our directions all work out. Okay. Now, we're going to look for both the car and the barge's actual speeds. We know that the car is moving relative to the barge at 4 meters per second. That's what that meant. I should have said that. Car moves relative to the barge at 4 meters per second. So if you're standing on the barge, you see it can go on that by at 4 meters per second. Okay? So let's say that the V car is equal to VB minus 4. Okay? Because car relative to the barge is going to the left, so that's in the negative direction. All right, now let's use momentum. We'll use the momentum of our system plus the sum of the integrals of f dt equals mv2 of our system. Okay? Well, it starts from rest, the beginning of the problem. So both particles are at rest, so we're going to start with 0. Now, what did I say about internal forces? If these forces act equal opposite on each other, they cancel out. So what's my integral of f dt? Some of those. That's going to be 0 too. So I just basically have ending momentum. All right? Ending momentum is actually equal to 0, isn't it? Because everything on that side of the equation is equal to 0. But we'll get to that. Let's talk about the momentum. We'll have the mass of the car times the velocity of the car plus the mass of the barge times the velocity of the barge. Okay? So I got two equations, two unknowns. All I have to do is just start plugging things in, and we can find out what the relative speeds are. All right? So I have, this is equal to, what did I say that is? 1.5 kilograms, so 1,500 kilograms. So I'll call that 1,500 VC, velocity of the car, plus 10, velocity of the barge. I'm sorry, 10,000. And over here, I have an equation for the velocity of the car, so let's go ahead and just plug that in. 0 equals 15,000, or 1,500, sorry, times VB minus 4 plus 10,000 VB. And I can solve that for VB is equal to 5.5217. That would be in meters per second. Okay. We plug that into this equation, we can find out what the car is. Velocity of the car is equal to minus 3.48 in meters per second. Okay, so not so hard. You just have to remember the relative equations. And like I said, they're not terribly hard to implement in one direction. You get a little bit more tricky in two dimensions, but we're going to talk about those too. All right, so let's talk about the momentum of the system. What did we start with? 0. What did we end with? 0. What is it in the beginning? 0. What is it in the end? 0. What is it in the middle?
Nobody cares.
That's true. Nobody does care. That's a good point. Nobody cares. But it's still a valid question. It stays 0 the entire time. Okay? Momentum is always 0 in this case. The system momentum. You got momentum of each individual person, particle, but not anything of the system. Okay? So let's say he's driving along at 4 meters per second, gets to the end of the barge, slams on his brakes. What's the momentum then? Of the system? 0. What's the speed of the barge at the end of that?
It stops.
What's the speed of the car at the end of that? Car slams on his brakes, so he's going 0 relative to the barge. So the speed of the car relative to the barge goes to 0 at the end of the, right before he falls off the end.
It's all zero.
Everything's still zero, right? If the car has zero relative speed to the barge, then these guys both have zero relative speed or absolute speed at the end of the problem. So when you get to the barge, at the end of the barge, you still have zero momentum of the total system, and both speeds are zero again. They've moved though, haven't they? The car moved from one end of the barge to the other, and the barge moved, at least that way, a little bit. Does that make sense? So how do we find out how far they moved?
Kinematics. Find out how long it took.
You could do, perhaps you could do a, so move 20 feet. The barge moved, or the car moved 20 feet. The barge moved some other distance, didn't it? But that was 20 feet relative to the barge, not 20 feet absolute. There's probably a variety of ways that you could approach that how far they moved equation, or that question. It wouldn't be a good speed velocity kind of thing. The reason is because you don't know if it's constant speed. You only got up to 4 meters per second, but you don't know how long it took, right? You don't know if you had constant acceleration. He may have taken all 20 meters to get to the end of the barge. You don't really know. All you know is he gets up to 4 meters per second. During the time of his acceleration, the momentum of the system is constant. And after he stopped, the momentum of the system is constant. So here's a way that I did it that may be of some help. I don't know. But somehow, if you wanted to find out how far they moved relative to absolute, you could have done this. Let's say that using moments, let's say that you have the barge like this and the car like this, and you know that the CG of the barge goes this way and the CG of the car goes this way. Okay, so the weight goes down. You can take a moment about the end and say that the moment about A, statics, is equal to minus the barge, which is 10,000. And let's say that its total is 20 meters. That's okay. 20 meters over 2. Right? That's the moment of the barge. And the car is minus whatever that is, 1,500 times 20. Okay? And those have to be equal to the resultant force times x bar. Right? Kind of like we did in class. The resultant force times x bar, so that'd be plus resultant force, which is the two of those. I'll just put, instead of putting the g's in here, I'll just use kilograms because it all works out the same. So this would be 1,550 times x bar. And we can find out what x bar is. That is the location of the center of gravity at the start. And so that x bar was equal to 11.304. So that's the location of the center of gravity at the beginning. That has to be the location of the center of gravity at the end, too, because the center of gravity had no external forces. The center of gravity of the system was not under any force, so it didn't move. All right? So when we find out what happened is, here's our new condition. Here's the barge, has displaced some distance, and now the car is right there. So now we have this distance x. The car has moved some distance there, and the x bar is still the same. Does that make sense? X bar to the center of gravity of the system is still the same? All right. So let's just calculate how far the barge moved. So I'll do another moment equation. Moment about A is equal to, well, now I have the barge center of gravity has moved 10 plus x. So the barge center of gravity is 10,000. 10 plus x. Right? That's where its center of gravity is now. And I'm saying the car is plus 1,500 times x. And that's equal to the same thing, 1150 x bar. And I can solve that for x and find out how far the barge moved. And the barge moved 2.608 meters. You may think that's convoluted, but maybe there's a simple way to do it, I don't know. But you might want to know how far it moved, okay? And that's one method. You could probably also do some other ratios. Is that fun? Or funny?
It's mine. I don't know how you would just come up with that on your own. It's like some
Well, it's just
super-
statics. You remember statics?
Yeah, I remember statics.
I know, that was like
I just
6
don't think I
months
would have
ago.
just thought of doing that on my own. I don't think I would have come up with that.
Well, maybe you can think of a different way that's easier. I don't know. This was the way I thought of it. That's the way my brain works. So, all right, let's do another problem here. Let's do. Let's do an exploding projectile. So here we have a projectile that is going straight at 600 meters per second until it has a premature explosion. Instead of exploding when it got to the ground, it exploded in midair. All right, and then you can see the pieces broke up. Piece A goes to the left, piece B goes to the right, and let's talk about what the masses are and see if we can come up with an explanation of what happened here. All right, so let's see. The mass before is equal to 4 kilograms. The mass of A is equal to 1.5 kilograms, and mass of B is equal to 2.5 kilograms. All right, so the heavier piece went forward, and the lighter piece got blown backward after the explosion. All right, let's see if we can do this with momentum. I don't think we have to use the relative equation on this one. We can just do conservation of momentum. It's one piece before and it's two pieces after. So that means the momentum before has to be equal to the momentum after. In this case, we do have momentum of the system. The center of gravity of the system still moves forward at 600 meters per second, even after the explosion. Okay, so let's do mv1 equals the sum of mv2. Okay? The integral of f dt is 0 here because the explosion is an internal force. Whatever the explosion did operated equal opposite as a function of time. The force is a function of time for blowing those two pieces apart. Okay. So let's define it. We'll have to do it i's and j's on this one, and you can see some angles. So let's do before. We have mv of the total only in the I direction, don't we? And then we'll have mv minus m va, and it will be, well, let's put it this way. mva, it'll have an angle, it'll be minus cosine 45i positive sine 45j. Okay? Everybody see that? The angle there? All right, let's talk about part of projectile B plus projectile B plus MVB. And its angles are got some positive in the x direction and some negative in the y direction. So it would be positive cosine of 30i minus sine of 30 in the j direction. All right? Everybody see how we do that? All right, so we just start plugging and chugging then. This is going to be, I can put some numbers in here, but let's just do the I direction. I'll do the I's first. So here I've got this one in the I direction. So that is mass of 4 kilograms times 600. So that is 2,400 in the I direction. This one in the I direction. Forgot that I. So this one, the mass here is 1.5 dA minus cosine 45 plus VB is 2.5 times cosine 30. Okay? That's our i's. Do the j's. The j's have nothing on this side of the equation, so that'd be 0. And that's equal to our I direction for A would be 1.5 VA, and that would be positive sine 45, plus 2.5 VB times negative sine 30. And we equate the i's and j's. And we separate them out, we solve for the unknowns and stick them in there. And you got two equations, two unknowns again. Everybody knows how to do that? We just took a quiz on it. Know how to equate the i's and j's. So I got VA is equal to 3153 meters per second. Whoa! That's high. And VB is equal to 2652 meters per second. So that's curious, isn't it? It approaches a hole at only 600 meters per second. It explodes into two pieces. And we got one of them going backwards at 3,000 meters per second, and the other one going forward at 2,000 meters per second. So it told me that that's a pretty big explosion that sent those pieces going that fast. So, I don't know. I'm not a projectile theorist, but I suppose if your round exploded in midair, it would probably do that. So, all right. Any questions about that? How to do two dimensions, two directions like that? Okay. So this is conservation of momentum. The system has some momentum. There's no external forces causing a change in the system's momentum, so we all the directions have to match at the end. All right, any question? Please, ask a question if that's not straight. Okay, let's do another one. Let's do one where we're back in one dimension again, just one direction. This is a real interesting one. And here we have a box that we're going to toss onto this cart. And it's going to, the box and cart are smooth, so there's no friction between the cart and the box when we toss it on there. So if there's no friction, again, this is kind of idealistic, and some people have a hard time with idealistic problems, but the reason we do idealistic problems is that it helps us set up the thinking, and then we can add the friction and that sort of stuff after we make it, after we understand the basics. And in many cases too, sometimes the small things, maybe friction is negligible, like a roller coaster. A roller coaster has friction, but not very much. Compared to the MGH and the 1/2 mv squared, friction on the wheels is pretty small. So you can almost ignore those things a lot of times. This one probably not so much, but what do we see here? Box is tossed onto the smooth cart, slides over, compresses the spring. Once the spring is fully compressed, what happens? What is the speed of the cart? Okay, so this is a really good momentum problem because we have beginning momentum and ending momentum of a system. Beginning momentum of a particle combines with the cart, and now we have ending momentum of the system. Okay, so let's do that. We'll say, now again, once it slides onto the cart, it slides, the cart is not moving because there's no friction on it. The box slides until it starts touching the spring. It compresses the spring, which probably starts making everything move, completes the compression of the spring, and at the instant the spring is fully compressed, whatever the fully compressed is, it has a speed, and that's what we're going to look for. The speed at the instant the spring is fully compressed. All right, so we don't have to take into account the spring's compression yet in this momentum problem because it's all internal. Whatever spring force is pushing the cart, as the spring gets compressed, it starts pushing the cart. The spring also pushes back on the box. So the integral of f dt of the spring is an internal force. is pushing equal opposite on the cart and the box. Okay? So we can ignore that. Or we can neglect it, I guess. It cancels. All right, so let's do our momentum. We'll say mv1 is equal to mv2, which is the sum of mv2. Let me put it that way. The sum of mv2. So what do I have for our beginning momentum? Well, the box says it has a 4 meters per second speed, but it's coming at an angle of 30 degrees. So we only consider the mv in the direction of motion. So it would be mv cosine theta. So how much is our, did I put on there? Box is tossed on there. How much does it weigh? 40 kilograms. Mass is equal to 40 kilograms. Okay, got to put that on there. All right, so I got 40 kilograms. That's my beginning mass. And I got 4 times cosine 30. That is all in the I direction. So I'm only going to do I's here because we don't really need to do J's, because at the end it doesn't have any J direction. Okay. After everything is fully compressed, I got the two masses together. So mass of the cart is how much? Mass of the box is 40. Mass of the cart is equal to 20. So once it's fully compressed, I got the mass of the box and the cart together. So that'd be 40 plus 20 times v2. I mean, that's super easy. Velocity of the cart is equal to 2.31 meters per second at that instant. Okay?
Simple.
That's simple. All right, so how much did the spring get compressed? That's the next part of the problem. The spring got compressed. Now we're back into energy. We have some beginning energy and some ending energy. So let's talk about that. Compression of the spring. Let's do T1 plus V1 plus U naught equals T2 plus V2. Okay? Our beginning kinetic energy of the box is 1/2 mv squared. The cart has no beginning kinetic energy, so that's 1/2 mv squared. There's no beginning potential energy because the spring is fully extended, and there's no gravity because it's going straight. So potential energy is 0. We said that there was no friction, and so that means that there's no work. So we have a beginning potential energy of just the box, which is this 1/2 m, and the velocity is still 4 cosine theta squared. But we'll get to that. At the end, what have I got? I have a 1/2 mv squared of our system. So I have 1/2 m1 plus m2, velocity squared, plus I have some compression of the spring, some 1/2 ks squared of the spring. That make sense? All right, so let's fill in the gaps. 1/2 mv squared, so I got 1/2, mass is 40, velocity is 4 cosine theta, 4 cosine 30, that is squared. Okay. And over here I got 1/2, got my two masses, so I got 60, and I've already solved for my velocity, it's 2.31 squared. And I have a spring. I have 1/2, and the spring constant is given, 1/2. And this says it is 6 kilonewtons per meter, so that's 6,000 kilonewtons per meter. And I can solve for S, and S is 0.163 meters. That's how much the spring gets compressed.
It's that long.
It's that long. It's 1 meter long spring. All right, what happens next? They spring apart. Now we need to find out the velocities of the two after they spring apart. So they have some energy now. We know how much energy they have. They have a 1/2 mv squared of the total system, and they have 1/2 ks squared of the total system. That's how much energy they have. And when they spring apart, they will release at least some of that energy. So let's talk about what that means. We're going to have to do a momentum and energy to solve for the end of it, too. So let's do the energy first, since we just talked about that. It starts with that beginning energy. After they spring apart, there's going to be 1/2 mv squared of each piece, and then spring goes back to 0. Okay? So did I solve for this? I guess I did not. So I'm going to have to write all these over again. Afterward, got T1 plus B1 plus U0. T2 plus B2. My beginning energy is now 1/2 60. 2.31 squared plus 1/2 6,000. And S is 0.163 squared. All right? That's the beginning energy of the system. Right before it springs apart. After it springs apart, it shoves them apart. All right? What do I end up with? I don't have any, well, I do have some potential energy. That's what that is. This is my kinetic energy of the system. This is the potential energy of the system. No work involved. At the end, I have a 1/2 mv squared of the box and a 1/2 mv squared of the cart. Okay? And if the spring actually gets fully uncompressed, then there's no spring energy left. All right, does that make sense? Now we plug it back into a momentum analysis to try and find out what we got. Because I can't do anything with that. I got one equation, 2 unknowns. I got the velocity of the box, velocity of the cart, nothing to really relate it. So let's put it back into a momentum equation now. So let's try with momentum. We got mv of our system equals sum of mv2. All right. So what's my beginning momentum? Well, my beginning momentum is I have this speed and that mass. So I go 60 times 2.31.
There's no friction, right? So won't they just equal each other?
Yeah, no friction.
So won't they just equal each other?
Say it again?
Won't they just equal each other?
They will, but we have different speeds. They're together as a system now, 60 with a common speed. As soon as they spring apart, the cart is going to go this way, the box is going to go this way. Or something, you know, they may both be traveling this way, I don't know. That's what we'd have to solve for. So, then I have the velocity of the box, so 40 times the velocity of the box, plus 20 times the velocity of the cart. So now I have 2 equations, 2 unknowns again. This is just a little bit tougher because I got a v squared here and a v squared here. I got these as v's and these as v's. So I think this is another solver approach. You may be able to do this by simplifying this and plugging that into here and multiplying it out, but I think solver would be a lot faster than it was for me. And so 2 equations, 2 unknowns for that, and you get these 2 values. Actually, so here, let me write all 4 values, and I want you to determine which values are correct. So the velocity of cart is equal to 4.62 or 0.00468, and the velocity of the box is equal to 1.155 or 3.4623. Okay, so when you solve this thing, you're going to get 2 sets of values. You'll get 2 values for A and 2 values for B. And you have to choose which one is the valid, appropriate answer. So looking at those 2 values for C and values for B, what would you choose? Velocity of cart is going to the right. I don't think there's any way that the velocity of the cart can go any place but to the right. So that's going to the right. The velocity of the boxes, both of those are positive, so it sounds like both of those are going to the right as well. I didn't get a negative number. But one of them is, one pair is right and one pair is wrong. So
Can you just plug it in and find that?
BC should be bigger.
well, they both satisfy the equations. That's the problem. They're both roots to this equation, but one's valid and one's not.
Well, yeah, BC has to be bigger.
So what'd you say, Brooke?
The velocity of the box is bigger than the cart, wouldn't it?
They'd be banging into each other, right? That's good insight. The velocity of the box cannot be greater than the velocity of the cart,
So we know that.
right? So we know that this pair is an invalid conclusion. This is the valid conclusion with the velocity of the box less than the velocity of the cart. Both going in the x direction.
I didn't know
Both
there were
positive.
pairs if I could like mix and match.
What's that?
I
I didn't realize they were pairs. I thought you like.
Well, that's the way your calculator will return it. It'll give you 4 values, and you just have to pick which ones. That makes sense.
But either way, the cart has to be going faster than what it is at the moment that they're compressed. So it has to be more than 2.31. And the box has to be going slower than that.
Yeah.
So it has to be.
Yeah, there's no way that the box could increase speed going from 2.31 up to 3.46 as a result of the spring. So,
Facts.
all right. Anyway, that's kind of a complicated one, but that's kind of fun. Let's do one more.
Homework.
What's that?
Yeah, 15 minutes.
Oh, I got to do this one. Then we'll do one more. This is taking longer than I thought, but I'm going slower than that. All right. So here's a cannon. It's firing a projectile. And the projectile is fired at 400 meters per second relative to the cannon. All right, so relative to, that is relative motion speed. We should be familiar with relative motion speed by now. So we need some masses here. What are the masses? Mass of the ball, mass of the projectile, I'll call it mass of P, is equal to 20 kilograms. And the mass of the cannon is equal to
20 or
250, no wait a minute, 20 kilograms. And this is 250 kilograms. All right? We're going to define a positive direction, so let's call going that way positive. All right, so in X, let's do our values in X, okay? Let's do MV1 is equal to MV2. What have I got in X direction? Well, I've got a, it says the cannon shoots a bullet relative to the cannon. So maybe I should write our relative equation too. The velocity of the projectile is equal to the velocity of the cannon plus the velocity of the projectile with respect to the cannon. This is where the 300 is, or the 400 meters per second. We don't know the actual speed of the projectile or the actual speed of the cannon, but we only know the projectile plus the projectile relative to the cannon, okay? All right, so let's do our momentum. In the X direction, mass times velocity, so I got 20 kilograms, and it goes 400 at some value. I don't know, how am I going to do that? I'll just put 200 times the velocity of the projectile in I. Well, hang on. That's right. The beginning momentum of the system before it explodes is 0. So it has no momentum. Sorry about that. All right, so after it explodes, the bullet's going to have some direction, and the cannon's going to have some recoil back there. So I'm going to say that this is, the mass of the projectile is 20 times VA projectile in the X direction, or V projectile in the X direction, plus 250 V of the cannon in the X direction. Okay? That's the I component. Does that make sense? Okay. Go ahead. We'll keep them both positive, and then we'll solve the positive and negative with the relative equation. Okay? That makes more sense to me than choosing that it goes negative. If it already says it goes relative to something in the negative, like we did on the barge, that makes more sense to put it as a negative. But this, I think you'll find that it'll be easier to keep the signs straight if you call everything positive, and then when you solve for them, you'll obviously discover one of them will be negative. Okay? All right, let's do the, so this is in the I direction. We've got the velocity of the projectile then, and this is the velocity of the cannon. So I can set this up as a relationship. I can say the velocity of the cannon is equal to minus 20 over 250 velocity of the projectile. Can't I? In the X direction. This is all in the I direction. All right, how about the J direction? j direction, we have, let's do the relative equation. So velocity of the projectile, that would be velocity of the projectile in the I direction, which I don't know, plus velocity of the projectile in the j direction, which I don't know, plus the velocity of the cannon in the I direction, which I do know that it only goes in the I direction because it's stuck to the floor. Then I got this, plus this goes 400 times cosine of 30 in the I direction plus sine 30 in the j direction. All right. Should have probably done that first. Okay, does that make sense? It's going off at a 30-degree angle relative to the cart, or relative to the cannon, going off at 400 meters per second. So the velocity of the projectile relative to the cannon is that. We know the cart is going backwards, but I'm going to keep it as a positive because we're going to solve for it being a positive. And then the velocity of the projectile is, we don't actually know it. All we know is that we know the velocity of the projectile is with respect to the cannon. Okay? So let's solve this then. Let's combine the i's and j's here. And here I got VP in the I direction equals 400 cosine of 30. Okay?
Is that VC supposed to be high?
Yeah. Say again?
The velocity of the cannon is supposed to be high instead of
Yes, thank you. That's what I messed up. The I plus the velocity of the cannon. All right, thank you. Now in the j direction. Actually, can I simplify this? I have the velocity of the projectile in the I direction is equal to VC, which I have over here, minus 20 over 250 times VP plus 400 cosine 30. Okay? So I can solve that. I can say that the VP in the I direction, velocity of the projectile in the I direction, is equal to 320.7, right? So I take that over there and evaluate that. 320.7 in the I direction. All right, now let's do the j direction. And we'll do homework. J direction. All right. In the j direction, I got the velocity projectile in the j direction equals V of the cannon sine 30. Okay. I'm sorry. I should say 400 sine 30, not V of the cannon sine 30. 400 sine 30. Right? In the j direction, that one plus that one. So 400 sine 30 is that. And that's equal to 200 meters per second. All right. So what have I got? By solving this only, I found out the speed of the projectile. The speed of the projectile is going 320 in the I direction and 200 in the j direction. It's not going at a 30-degree angle. It's actually going at a different angle. It's going 320 in the I direction, 200 in the j direction. So we can find out what the actual speed is of the projectile and the angle that it goes down. So let's find out what that is. All right. So let's say that the speed of the cannon, or speed of the projectile, v of the projectile, is equal to the square root of 320 squared plus 200 squared. And that's equal to 378 meters per second. And theta is equal to the 10 minus 1 of side opposite over the side over to side adjacent. So that's 200 over 320. And so theta is equal to 31.8 degrees. All right, so that's kind of interesting. Because it recoils, the speed of the cannon, or speed of the projectile, is less and goes up at an actually different angle.
Makes sense though.
I guess it kind of makes sense, but boy, if you were a howitzer operator out there on the field and said, well, I'm just going to aim at 30 degrees, and it ends up having less in a different angle, you're not going to hit your target. So I guess it has to take all that stuff into account. So, all right, so now that we found out what the relative speeds are, we can go back and find out what the recoil of the cannon is. We don't need to do that. So, how's that feel? I's and J's, momentum. We didn't really use momentum too much except for this relationship. But that worked in the I direction. We just plug that into the relative equation. Yeah.
And the angle is less, actually.
How much is it?
It's 28.4.
Is it 28? Did I do that wrong? 200 over 320 is 28?
Yeah.
Okay, well, big part then, 28. Well, still not 30, but, all right, 28 degrees. No, calculator doesn't work. So. Okay,